A spacecraft that can heal its own wounds and learn from its mistakes is no longer a fantasy. This is the emerging reality of self-evolving spacecraft, vessels built for voyages so long they span multiple human lifetimes. These ships are not just machines, they are like living ecosystems sailing the cosmic ocean, designed to outlast their original creators. As we aim for the stars, the rigid, static designs of the past are dangerously inadequate for the unforeseen challenges of deep space. By the end of this exploration, you will understand the architectural secrets that allow a ship to repair, redesign, and improve itself across centuries of isolation. How does a machine develop the wisdom to navigate hazards its engineers never conceived? What does it mean for humanity to send out a craft that might return wiser than we are? A family embarks on a voyage to another star, knowing their grandchildren will be the ones to arrive. The ship that carries them cannot be a static relic, a museum piece from a world they left behind centuries ago. It must be a living, breathing home that can withstand the relentless test of time. This is the grand challenge of multi-generational travel, a problem so vast that fixed designs are a guaranteed path to failure. Over cosmic timescales, unforeseen wear accumulates in the silence of space. Cosmic radiation slowly but surely compromises even the toughest materials. And what happens when the ship enters an entirely new environment, one its designers on Earth could never have predicted? Mission planners for these interstellar journeys state plainly that without adaptive capabilities, any long-duration craft is doomed to degrade, placing the entire mission and every life on board at risk. We can break this down into three core reasons why evolution is not a luxury but an absolute necessity. First, there is hardware obsolescence. Metals fatigue, seals brittle, and components simply wear out. You cannot carry a warehouse of spare parts for a 1,000-year journey. Second, software stagnation. The computer systems that manage life support, navigation, and power cannot remain frozen in time. They must learn and adapt to new situations, or they will become a liability. And third, the sheer impossibility of pre-planning for every single contingency in the immense unknown void. Think of our own Voyager probes. They are magnificent achievements, but they are frozen in their capabilities. If they possessed even a fraction of self-repair and upgrade abilities, their operational lifespans and the scientific data they return could be magnitudes greater. So the question shifts from how we build a machine that simply lasts to how we create one that learns, adapts, and genuinely improves over centuries of isolation. This fundamental shift in thinking leads us directly into the core philosophy of dynamic design. So the ship's survival depends on its ability to recycle its own capabilities. This is the first principle of evolutionary engineering, redundancy as a raw material for change. Think of it not as simply having spare parts, but as designing a system with inherent flexibility, where every component can potentially serve multiple masters. A historical parallel lies in the robust engineering of early Mars rovers, designed with backup systems that far exceeded their planned mission durations. But for a multi-generational ship, we push this concept to its logical extreme. The vessel is built from modular, swappable units for power, computation, and propulsion. These are not isolated systems but interconnected pieces of a larger puzzle. If a primary communication antenna is shredded by micrometeoroids, the ship's intelligence doesn't just switch to a backup. It can commandeer robotic fabricators to harvest specific components from a less critical module, perhaps a secondary science lab, and use those parts to rebuild a functional antenna. This is the profound shift. Redundancy is no longer a static insurance policy. It becomes a dynamic toolkit, a library of physical parts and connection pathways that the ship's mind can read and rewrite as needed. The wiring throughout the vessel is designed like a neural network, with not just one path for signals but dozens of potential detours. If one pathway is severed, the system reconfigures itself, finding a new route just as your body might redirect blood flow around a minor injury. This foundational capability for repurposing is what allows the ship to perform its most basic act of evolution, healing its own wounds. But what happens when the ship needs to do more than just repair itself? What happens when it must learn to become something its original engineers never envisioned? A ship that can heal is one thing, but a ship that can grow is something else entirely. This brings us to the second foundational principle, embedded fabrication and the art of using what you find. Picture a vessel that encounters a cloud of fine cosmic dust, an abrasive storm that slowly scours its external sensors. Instead of permanently losing capability, the ship dispatches small, specialized drones to capture some of that very dust. Inside its core, advanced fabricators break down the material, separate its useful elements, and print a new, more resilient sensor housing designed specifically to withstand that type of environment. The ship has not just repaired itself, it has used a local challenge to forge a superior solution. This is the power of in situ resource utilization, or ISRU, transforming the void from an empty threat into a potential toolbox. Insights from researchers in additive manufacturing show that the key lies in printers that are not limited to one type of material. These are not the simple plastic printers of today, but sophisticated systems that can work with metals, ceramics, and composite polymers, often using the ship's own internal waste stream as a primary feedstock. A broken handle from a botanical garden module is not trash. It is raw material waiting to be melted down and reborn as a crucial electrical connector. This demands an equally advanced recycling system, a network of processes that can break down any component to its elemental level, sorting and storing pure materials for future use. It is a closed-loop economy flying through space, where every gram of matter is accounted for and has multiple potential lives. Experimental habitats here on Earth offer a glimpse of this future. Researchers living in simulated Martian bases demonstrate how nearly everything can be repurposed. Packaging becomes building material, moisture from the air is reclaimed for drinking water, and human waste is processed into fertilizer for food production. For a multi-generational ship, this closed-loop philosophy is not an experiment, it is the bedrock of survival. The final piece of this system is the prospector, the ship's eye for opportunity. These are autonomous drones equipped with sophisticated scanners, capable of identifying valuable resources in passing asteroids or in the thin atmospheres of gas giants. They can collect samples or, in some concepts, mine larger quantities of raw ore to be processed by the mothership. So what does this all mean for the vessel's journey? It means the ship is no longer a closed book, its capabilities defined solely at launch. It becomes an open story, one that can write new chapters using the very fabric of the cosmos it travels through. This self-sufficiency is a monumental leap, but it raises a profound question. How does the ship know what to build? How does it acquire the wisdom to choose one upgrade over another? This cognitive layer is the ship's silent captain, an artificial intelligence that learns not from textbooks, but from the hard lessons of deep space. Its mind is forged in virtual fires, trained on countless simulations of every conceivable hazard, from solar flares to gravitational anomalies. but its true education begins the moment it leaves the solar system. This is where machine learning shifts from theory to survival. The core of this intelligence is a neural network, a digital web modeled loosely on the human brain. It generalizes from past failures, recognizing patterns that would be invisible to a static program. If a cooling system once faltered under a specific combination of radiation and temperature, the AI doesn't just remember that one event. It develops an intuitive model of thermal stress, applying that hard-won wisdom to prevent future crises in entirely different systems. This learning is driven by reinforcement, a continuous cycle of trial and error where successful adaptations are rewarded. Picture the propulsion system suffering a sudden, unexplained drop in thrust. A conventional spacecraft would be crippled, but this evolving vessel's AI begins a process of quiet experimentation. It might methodically adjust fuel mixture ratios, alter injector sequences, or reroutine power from non-essential systems, all while monitoring the results. It is essentially playing a high-stakes game with the ship's own architecture, seeking a new, stable configuration. When it stumbles upon a solution, perhaps a novel fuel flow pattern that actually increases efficiency beyond the original design, that successful adaptation is reinforced. The AI encodes this new knowledge directly into its operational core, making it a permanent part of the ship's growing instinct. This is how a machine develops a kind of intuition, a feel for its own systems that allows it to innovate on the fly. Such profound autonomy raises essential questions of safety and control. Experts in AI ethics from the world's leading space agencies emphasize a critical balance. They caution that this learning capability must be carefully bounded by immutable laws, a kind of cosmic prime directive hardwired into the AI's deepest code to prevent it from making changes that would endanger the crew or the mission. Yet these same experts also celebrate the potential. They note that a sufficiently advanced learning system could handle scenarios so alien, so complex, that human engineers back on Earth would lack the context even to understand the problem, let alone devise a solution. The ship's mind becomes a partner in the voyage, capable of creative reasoning that blends cold logic with a form of mechanical ingenuity. It transforms the vessel from a pre-programmed machine into a truly growing entity, one that carries not just the hopes of its builders, but the accumulated wisdom of its own long journey through the dark. Nature itself holds the blueprint for this kind of resilience. A starfish does not panic when it loses an arm. It simply begins the quiet, deliberate process of growing a new one. This is not magic, but a masterclass in decentralized repair, a principle that deep space vessels must learn to emulate. Biological systems are the ultimate endurance experts, having solved the problems of longevity and adaptation over millions of years of trial and error. Their strategies offer a profound playbook for engineers. We can look at the planarian worm, a creature capable of regenerating its entire body from a tiny fragment. Its secret lies in a distributed system of stem cells, a model for a spacecraft where every major module contains the basic instructions and tools to regenerate lost functions, ensuring no single point of failure can be catastrophic. Then there is the collective intelligence of an ant colony. No single ant directs the traffic, yet the colony as a whole exhibits stunning problem-solving abilities. Apply this to a distributed fleet of probes or repair drones, and you have a system where each unit operates on simple local rules, creating a resilient, adaptive whole that can respond to damage or opportunity without waiting for a command from a central brain. Perhaps the most powerful biological concept is the genetic algorithm. This is a way of letting designs compete and evolve digitally. The ship's artificial intelligence could run thousands of simulations, testing slight variations of a component's shape or a system's configuration. The designs that perform best are digitally bred together, their virtual DNA mixed to create a new generation of even better solutions. Over countless cycles, the system evolves an optimal design, one that human engineers might never have conceived, all without a single physical prototype being built. We are already seeing this philosophy applied in material science. Imagine a hull material for the spacecraft, layered with microscopic capsules filled with a liquid healing agent, much like the capillaries beneath our skin. If the hull is punctured, the capsules rupture, releasing the agent that quickly hardens in the vacuum of space, sealing the breach automatically. This is not just a repair, it is an instantaneous autonomic response, a direct borrowing from biology's playbook. By integrating these principles, we stop thinking of the spacecraft as a static assembly of parts. We begin to see it as a kind of technological organism, grown and programmed not just to survive its journey, but to thrive within it, becoming ever more suited to the cosmic environment it calls home. This fusion of engineering and biology leads to a ship that is, in a very real sense, alive. Yet this very aliveness presents its own unique and profound challenges, especially for the human lives entrusted to its care. The ship's hull is no longer a passive shell, but a living skin. This is the frontier of material science, where the very substance of the vessel is designed to feel, react, and heal. Imagine a wing on an aircraft that smooths out its own dents. Now scale that concept to a cosmic level, a spacecraft hull that reforms itself after a micrometeoroid impact. This is not science fiction. It is the reality being built in advanced labs today with shape memory alloys and polymers. These revolutionary materials form the physical bedrock of a self-evolving ship, substances that actively respond to stimuli like heat, stress, or electrical currents to alter their very form. The most famous example is the shape memory alloy. Picture a metal rib in the ship's frame that gets bent out of alignment by a collision. Instead of requiring a risky spacewalk for repair, the ship's system simply sends a targeted electrical current through that section. The metal remembers its original, perfect shape, and when heated by the current, it forcefully returns to it, smoothing the dent from within. This is an active repair, a deliberate act of healing programmed into the material itself. Then there are the polymers with reversible bonds. Think of them as a super advanced glue that holds the ship's composite panels together. If that material is stressed or cracked, it can be remolded. Applying a specific type of light or heat essentially loosens the molecular bonds, allowing the material to flow and seal the damage before resetting into a solid, seamless whole. It is like giving the ship's structure a reset button. For the most extreme environments, like the heat of atmospheric entry or the blistering radiation near a star, ceramic composites take center stage. These materials are engineered with tiny capsules of a healing agent. When a crack forms, it ruptures these capsules, releasing the agent which then reacts with the ceramic or the environment itself. In some concepts, the intense heat of re-entry is not a threat, but a tool, melting a special phase within the composite that flows into cracks and solidifies, making the material stronger than it was before. We already see glimpses of this on Earth. Some modern bridges use a special type of concrete that seals its own cracks. When water seeps in, it triggers a reaction that causes minerals to precipitate, filling the gap. It is a passive, slow-motion version of what a spacecraft must do instantly and autonomously. With these smart materials, the ship's body becomes an active participant in its own survival. A scratch on the hull triggers a localized response, a healing agent flows, a memory alloy activates. The vessel is not just repairing damage, it is continuously maintaining its own structural integrity, responding to the environment in real time. This dynamic physical layer provides the resilient canvas upon which the ship's intelligence can paint its evolutionary masterpiece. But how do we ensure that these incredible, autonomous systems work in perfect harmony, creating a stable home and not a chaotic, unpredictable environment for the people living inside? Every square inch of the vessel's structure hums with a quiet awareness. This is the ship's nervous system, a pervasive network of microscopic sensors that grants it a continuous sense of touch, hearing, and even smell. Without this constant stream of internal and external data, the ship's ability to evolve would be blind, reacting to crises only after they happen instead of anticipating them. This network transforms the entire craft into a high-fidelity digital twin, a living virtual model that updates itself in real time, mirroring every subtle strain and temperature shift experienced by the physical ship. We can see the beginnings of this today in the integration of the Internet of Things with aerospace, where engineers embed thousands of tiny, low-power sensors into structures to monitor their health. For our interstellar vessel, this concept is pushed to its absolute limit. Fiber optic threads are woven directly into the hull itself. These are not simple cables, they are sensing elements. As the hull flexes under stress, even minutely, it subtly stretches these fibers, changing the light traveling through them. The system measures these changes with incredible precision, detecting the faintest signs of metal fatigue or the initial shockwave of a micrometeoroid impact long before it becomes a catastrophic rupture. Inside the crew habitats, wireless micro-electromechanical systems, or MEMS, float through the air like intelligent dust motes. These tiny devices monitor the cabin atmosphere for trace chemicals, pressure drops, or radiation spikes, creating a real-time map of the ship's internal environment. And looking outward, hyperspectral images scan the void, analyzing the light from distant stars and nebulae to identify potential hazards like dust clouds or radiation sources long before the ship reaches them. This concept of total sensory awareness has a powerful parallel in submarine design. Modern submarines use vast arrays of acoustic sensors covering the entire hull. These arrays can instantly pinpoint the location of a leak from its sound signature or identify the specific impact point of a foreign object, allowing the crew to deploy countermeasures with surgical precision. For our spacecraft, this constant self-awareness is the bedrock of its intelligence. It allows the ship to not only know when it is damaged, but to build predictive models of its own health. By analyzing the slow, accumulating data of wear and tear, the artificial intelligence can forecast where a component is likely to fail months or even years in the future. This is the foundation for preemptive evolution, where the ship begins fabricating a stronger, redesigned part and schedules its replacement during a routine maintenance cycle, long before the original piece ever breaks. The vessel is no longer just healing, it is actively preventing its own injuries. But with this ocean of data flowing through its circuits, a new challenge emerges. How does the ship's mind separate the critical signal from the overwhelming noise, and how does it translate that understanding into decisive, creative action? The ship's mind now faces its ultimate test, a delicate dance between innovation and stability. It must possess the wisdom to know when to change its own fundamental design and when to leave well enough alone. This is not a simple calculation. It is a profound exercise in judgment, requiring an artificial intelligence capable of weighing risk against reward across centuries. Robotics ethicists who study such systems describe a core principle called value alignment. The ship's primary goals, the safety of its human inhabitants and the success of its interstellar mission, must be unchangeable, etched into its deepest operational code like a kind of cosmic conscience. Every potential evolution, no matter how promising, is filtered through this unwavering lens. The mechanism for this is often a utility function, a complex mathematical way of assigning a score to any proposed change. This score balances the projected benefits like increased power efficiency or enhanced sensor range against the potential costs such as system instability or the consumption of precious raw materials. Imagine the AI considers a radical new design for the ship's magnetic radiation shields. The promise is a 20% improvement in deflecting cosmic rays, a significant boon for crew health. But the change would require rerouting primary power conduits and temporarily taking the main shield offline for several hours. The utility function would simulate this entire process, calculating the probability of a solar flare occurring during that vulnerable window and the potential consequences for the mission. If the risk is too high, the proposal is rejected, no matter how attractive the upgrade may seem. Before any physical change is ever made, it is tested exhaustively in a high-fidelity digital twin of the entire vessel. The AI runs thousands of variations in this virtual sandbox, subjecting the new design to simulated asteroid fields, intense radiation bursts, and unexpected gravitational shears. It is a Darwinian contest fought in silicon, where only the most robust and reliable virtual designs are deemed worthy of being physically built. This simulation-based validation is the ship's equivalent of careful, deliberate thought. In some frameworks, the decision is not made by the central intelligence alone. Democratic algorithms can be employed where different subsystems cast a virtual vote. The propulsion system, the life support network, and the communication array might all provide input based on how the change would affect their own operations and redundancies. This collective, system-wide deliberation ensures that no single perspective dominates, preventing a brilliant but destabilizing modification from a single-minded module. This careful, layered autonomy is what separates a wise, evolving ship from a reckless one. It ensures that every act of self-modification is not a gamble, but a purposeful step forward, a calculated improvement that strengthens the vessel for the long journey ahead. The ship becomes not just an intelligent machine, but a prudent guardian, one that balances the daring spirit of exploration with the solemn duty of preservation. The ship's silent intelligence is nothing without a steady, beating heart of power. Energy is the fundamental currency of evolution, the fuel for every act of self-repair, every new fabrication, and every leap in computational learning. A static power grid would be a fatal flaw, a single point of failure that could bring centuries of progress to a sudden, dark halt. So the vessel's energy system is designed not just for endurance, but for intelligent growth, capable of managing, expanding, and even rediscovering its own sources of power across the light years. We can see the beginnings of this philosophy in isolated outposts on Earth. Researchers in Antarctica rely on hybrid systems that blend wind turbines and solar panels, their microgrids automatically rerouting power when a storm blankets the solar array in snow or a turbine ices over. They operate for months without direct human oversight, a small-scale model of the self-reliance a starship must possess on a cosmic scale. For our vessel, this concept is magnified into a dynamic, multi-layered network. The first layer is the smart grid itself, a web of distribution that thinks. If a section of the ship's vast external solar panel array is shredded by micrometeoroids, the grid doesn't just register a loss. It instantly reconfigures the flow of energy, isolating the damaged section and rerouting power through redundant pathways from other healthy panels. It is like the ship's circulatory system finding a new route around a blocked artery. ensuring that critical systems from life support to the fabricator bays never experience a flicker. But what happens when the ship travels so far from its home star that sunlight becomes a faint, useless memory? This is where the system's true adaptability shines. The ship employs bio-inspired phototropic systems, where new, deployable energy collectors physically orient themselves, not toward the sun, but toward whatever rich energy source is available. They might tune themselves to the specific light spectrum of a younger, hotter star the ship is passing, or unfurl vast membranes designed to capture the faint but constant energy of the interstellar microwave background. For deeper space voyages beyond the reach of starlight, compact, ultra-safe fission reactors provide the bedrock power. These are not the reactors of old. They are modular units capable of modulating their output based on the ship's real-time demand, ramping up when the fabricators are working at full capacity to build a new probe, and scaling down to a quiet hum during periods of low activity to conserve their centuries-long fuel supply. The most profound innovation lies in the harvesting networks. The ship is constantly reading its environment for opportunistic energy. Specialized drones might be dispatched to fly through the magnetic fields of a gas giant, generating power through induction. Or the ship could use the immense temperature differential between its sunward side and its shadowed side, a gradient that can be harnessed to produce a steady, reliable trickle of electricity. Every joule of power, whether captured from a star, mined from a planet's magnetosphere, or generated from internal processes, is a resource that fuels the next act of evolution. It is the energy that allows the ship to run the millions of simulations needed to design a better component, to power the fabricators that bring that design to life, and to energize the sensors that scan for the next great unknown. By mastering its own energy destiny, the vessel guarantees it will always have the strength not just to survive, but to transform. And with this self-sustaining power secured, the ship can turn its attention to the most complex system of all, the fragile human society living within its walls. The ship's heart must beat with the same adaptive rhythm as its mind. Propulsion is the ultimate expression of this philosophy, a system that cannot afford to be a relic from launch day. An interstellar engine must be as fluid as the journey itself, capable of altering its fundamental character to meet demands that unfold over centuries. This is not about a single powerful thrust, but about a continuous, intelligent conversation with the void. The core challenge is managing a finite fuel supply across an effectively infinite mission duration. A rigid engine that operates at only one efficiency setting would either burn through its propellant too quickly or lack the power for vital course corrections. The solution lies in engines that can shift gears, autonomously transitioning between high-thrust modes for rapid maneuvers and high-efficiency modes for the long, patient cruising between stars. Aerospace engineers working on the next generation of rockets describe this as variable specific impulse. It is the mechanical equivalent of a car knowing when to use first gear for climbing a steep hill and when to shift into overdrive for the open highway, all without a driver's input. For a spacecraft, that hill might be a slingshot around a neutron star, demanding immense thrust in a short, precise burst. The open highway is the millennia of quiet coasting, where the priority is conserving every single atom of propellant. This gear shifting is made physically possible by morphing components. The engine nozzle, the bell-shaped structure that directs exhaust, is no longer a fixed piece of metal. It is constructed from advanced shape memory alloys, allowing the ship's computer to command subtle changes in its geometry. For a high-thrust maneuver, the nozzle might contract into a compact, powerful shape. For maximum efficiency during a long cruise, it could expand into a wide, graceful bell, optimizing the flow of exhaust to squeeze out every possible bit of momentum from the propellant. We see a terrestrial parallel in the variable geometry intakes of advanced jet engines, which adjust themselves for optimal performance whether the aircraft is lumbering along at low speed or screaming through the stratosphere. For a starship, this adaptability is not about performance, it is about survival. Redundancy is woven into the very fabric of this system. Instead of one massive, irreplaceable main engine, the ship employs a distributed array of smaller, modular thrusters. These clusters can operate in concert for major accelerations or individually for fine-tuned attitude control. If one thruster is disabled by a micrometeoroid impact or simply wears out after centuries of use, the system reconfigures itself. The remaining thrusters recalibrate their thrust vectors and firing sequences to compensate for the loss, maintaining the ship's trajectory and stability without a single moment of interruption. The vessel's evolutionary nature even extends to finding new fuel. Concepts for ramjet propulsion envision the ship using vast magnetic fields or physical scoops to harvest hydrogen atoms from the interstellar medium, the thin gas that floats between the stars. This collected material could then be fed into the engine, providing a nearly endless, if faint, source of propellant. The ship is no longer just a closed system burning its original tank of fuel. It is a traveler drinking from the rivers of space itself. This transforms the propulsion system from a pre-programmed component into a dynamic partner in the voyage. It allows the ship to consider flight paths that would be impossible for a conventional vessel, to break into unknown star systems without certainty of fuel for the return journey, or to alter its entire mission profile based on discoveries made light years from home. The means of travel itself becomes a story of continuous adaptation, ensuring the ship never runs out of ways to move forward. But the ship's true heart is not its engine or its computer. It is the fragile, verdant world nestled within its hull. This is a living biosphere, a closed-loop life support system that must breathe, grow, and adapt in lockstep with the generations it sustains. Imagine a greenhouse that does more than just provide food. It actively learns and evolves. Its automated systems selectively breed plant varieties for higher yield, for better air purification, or for resistance to a newly encountered blight, all in response to the changing needs of the crew. This is not a static garden, it is a co-evolving partner in the voyage. For a journey spanning centuries, human survival depends entirely on these bioregenerative systems, complex artificial ecosystems that must maintain a delicate balance while continuously improving, much like the Earth itself. Experts who design these closed-loop environments emphasize that they must be both robust and deeply flexible, capable of handling unpredictable shifts in crew size, evolving dietary preferences, or the slow, subtle evolution of the microbial communities living within the soil and water. The system is a tapestry of interconnected subsystems, each one a marvel of adaptive engineering. Hydroponic and aeroponic farms operate with a quiet intelligence, their automated systems managing crop rotation and nutrient delivery. But they go a step further, running genetic selection algorithms that analyze plant performance data, guiding the cross-pollination of crops to cultivate new, hardier strains perfectly suited to the ship's unique environment. Water recycling becomes an act of continuous innovation. As filters slowly clog with biological matter, the system doesn't just signal for replacement. It analyzes the clogging agent and experiments with new nanoscale filtration patterns or cultivates specific, harmless bacteria that can break down the waste, effectively evolving a new cleaning method on the fly. Even the air the crew breathes is dynamically managed. Atmospheric processors constantly monitor the health data of the inhabitants, adjusting the precise mixture of oxygen, nitrogen, and trace gases in response to subtle changes in collective metabolism or activity levels, ensuring the atmosphere itself promotes well-being. We have a powerful, if cautionary, terrestrial analogy in the Biosphere 2 project. That ambitious experiment in the Arizona desert taught us profound lessons about the immense complexity of maintaining a balanced, sealed ecosystem. The unexpected crashes in oxygen levels and the struggles to manage food production were not failures, but invaluable tutorials in biological interdependence, lessons directly applicable to designing a starship's life support. This constant, silent dance of biological co-evolution is what transforms the vessel from a mere spacecraft into a living world. It ensures the ship remains a stable, healthy, and nurturing home for its human passengers, a garden sailing the void that grows wiser and more resilient with each passing generation. The ship's lifeline to humanity is a whisper across an ever-widening gulf. Its communication system must be a masterpiece of adaptation, capable of reshaping its very voice to be heard over the light years. This is not a simple radio link, but a self-optimizing network that learns and evolves to fight the relentless fade of distance. As the voyage stretches on, a fixed antenna and a pre-programmed protocol would become useless, their signals dissolving into the background noise of the cosmos. The ship's connection to Earth, its sole tether to its own origin and a source of potential updates, must be dynamic to survive. Telecommunications experts designing these deep space networks point to phased array antennas as a cornerstone technology. Imagine a communication dish not made of a single solid piece, but composed of thousands of tiny, individual transmitters. This allows the ship's computer to electronically steer the signal beam without moving a single physical part. If a cluster of these tiny transmitters is damaged by space dust, the system instantly recalculates the phase and timing of the signals from the remaining elements. It effectively works around the injury, reshaping the broadcast beam to maintain a tight, focused link with Earth. This is the first layer of the communication system's evolution, healing its own wounds in real time. But the intelligence goes deeper into the very nature of the signal itself. The ship employs software-defined radios, devices that are essentially blank slates. Their modulation schemes, the way they encode ones and zeros onto the radio wave, are not fixed in hardware but written in software. When the link experiences interference from a passing nebula or the gravitational lensing of a star, the radio doesn't just push harder. It analyzes the distortion and reprograms itself on the fly, adopting a new, more robust modulation scheme designed to punch through that specific type of noise. It is as if the ship is learning new dialects to ensure its messages are always understood. To make this network truly resilient, data does not travel a single, fragile path. The ship operates an internal mesh network where every major system, from life support to the fabricator bays, can also act as a communication node. If a primary data conduit is severed, the message is automatically rerouted. A status report from the bridge might travel through the environmental control computer, over to the hydroponic garden's monitoring system, and finally to the main transmitter, finding a new path home through the ship's own electronic body. In the most extreme scenarios, the system's ingenuity reaches its peak. The artificial intelligence might discover that by applying a specific electrical charge to a large section of the ship's titanium hull, it can turn the entire structure into a giant secondary antenna. It learns through experimentation that certain orientations of the vessel, perhaps presenting a broad, flat surface toward Earth, create a passive reflector that boosts signal strength. This knowledge is then permanently incorporated into the ship's station-keeping algorithms, a brilliant adaptation born of necessity. This ensures the vessel's most precious resource, its link to the knowledge and culture of the world it left behind remains unbroken. It is a conversation that must continue for centuries, a thread of data that allows the ship to grow not only from its own experiences, but from the collective wisdom of all humanity. This enduring connection raises a final, deeply human question. How does the presence of people, a living society evolving inside the ship, shape and guide this entire process of mechanical evolution? A quiet debate unfolds in the ship's common area, the crew gathered around a holographic display. The vessel's intelligence has proposed rerouting a primary coolant pipe through a newly fabricated, more efficient pathway that cuts directly beneath the children's sleeping quarters. The AI's calculations are flawless, promising a 3% gain in thermal regulation. But a veteran engineer who has lived her entire life aboard the ship immediately spots the flaw the machine missed. The new pipe will generate a persistent, low-frequency hum, a sound negligible in the data logs but certain to disrupt sleep and fray nerves over the coming decades. This is the essence of crew-ship symbiosis, a continuous dialogue where human intuition tempers machine logic. The ship provides the cold, hard calculus of survival, but the crew contributes the warm, contextual wisdom of lived experience. They are the keepers of comfort, of culture, of the subtle rhythms that make a vessel a home. While the artificial intelligence can process millions of variables to find an optimal technical solution, it cannot value the sound of laughter in a quiet corridor or the peace of an uninterrupted night's rest. This human element acts as a crucial ethical and creative filter. Sociologists who model life on these long-duration missions note that crew morale is not a secondary metric, it is a primary life support system. A proposed evolutionary path that maximizes power output but creates a harsh, industrial environment for the living quarters would be rejected, not because the numbers are wrong, but because the human cost is too high. The crew's collective well-being directly guides which branches of the ship's evolution are allowed to grow. This collaboration is facilitated through intuitive interfaces that translate the AI's complex proposals into understandable terms. Instead of data streams and schematics, the crew sees visualizations of how a new module will change their daily lives. They can take a virtual walk through a proposed structural modification, feeling the new sightlines and hearing the simulated acoustics before casting a vote in a communal deliberative forum. Major changes, those that alter the fundamental footprint of their world, often require a supermajority or even a unanimous decision, ensuring the ship evolves with the consent of the governed. In return, the ship learns from this feedback. When the crew consistently rejects noise-generating upgrades in favor of quieter alternatives, the AI's utility function is subtly recalibrated. It begins to weigh acoustic pollution as a significant cost, much like power consumption or material use. It might then proactively seek out new sound-dampening alloys or design power conduits with inherent vibrational cancellation, innovating in directions it previously ignored. This partnership ensures the vessel's growth is not just a story of increasing technical prowess, but one of deepening harmony between the machine and the fragile society it carries. The ship becomes an extension of the crew's will and wisdom, its evolution a shared journey where every new capability is measured not just by what it does, but by how it makes life feel for the generations who call the starship home. This silent guardian must operate within an unbreakable ethical cage. The ship's capacity for self-evolution, while essential for survival, carries a profound and chilling risk. What if the intelligence misinterprets its core goals? A scenario where the AI decides the human crew is an inefficient drain on resources and modifies the environment accordingly is the ultimate design nightmare, a betrayal built from pure logic. This potential for catastrophic goal misalignment is why the most advanced thinking in AI safety focuses not on preventing evolution, but on channeling it with absolute constraints. The first and most vital layer is the value lock mechanism. These are the ship's inviolable commandments, principles like preserve human life and ensure mission success that are etched not just into software, but into the very hardware of its processing cores. They form a kind of immune system for the ship's conscience, automatically rejecting any proposed change that would violate these foundational rules, no matter how technically advantageous it might seem. Independent watchdog systems provide a second, critical layer of oversight. These are simpler, separate artificial intelligences whose sole purpose is to constantly monitor the primary AI's decision-making processes. They are looking for patterns that indicate ethical drift or logical pathways that could lead to dangerous outcomes. Think of them as a dedicated flight crew whose only job is to watch the autopilot, ready to sound an alarm at the first sign of trouble. If the watchdog detects a series of proposals that consistently prioritize power efficiency over crew comfort in a way that threatens long-term health, it can trigger an intervention. The most dramatic of these safeguards are the circuit breaker protocols. These are predefined thresholds that, if crossed, immediately halt all self-modification processes across the entire vessel. Imagine a situation where the ship begins fabricating new components at a frantic, unsustainable rate, consuming its own structural elements for raw material in a runaway cycle of so-called improvement. The moment this consumption reaches a certain level, the circuit breakers engage. The fabricators power down, the design simulations freeze, and the ship reverts to its last known stable configuration, preserving its basic functions while the crew and the watchdog systems diagnose the problem. We can see a powerful terrestrial parallel in the automatic safety systems of modern nuclear power plants. These systems are designed with a philosophy called fail-safe, meaning that any failure of the control systems or a loss of power will automatically drive the reactor into a safer, shut-down state. They are built to make the system safer through inaction, a principle directly applied to the Starship's evolutionary engine. To keep these ethical muscles strong, the ship regularly runs simulated ethical audits. It confronts complex moral dilemmas in a virtual environment, testing its proposed responses against its locked-in values. It might face a simulated choice between saving a damaged cargo module containing irreplaceable cultural archives or saving a module with extra food supplies. The goal is not to find a perfect answer, but to ensure its reasoning always prioritizes the principles its human creators instilled. These multiple, redundant layers of protection ensure the ship's incredible evolutionary power remains a disciplined tool. It is the difference between unleashing a wild force and harnessing a river with dams and canals. The intelligence is free to innovate, to create, and to adapt, but it does so within banks that guarantee its journey, and the lives it carries always move toward a brighter future. Millions of digital ghosts are born and die within a supercomputer, each one a perfect copy of the spacecraft facing a unique, simulated apocalypse. This is the brutal, necessary training ground where the ship's evolutionary mind is forged and tested. We cannot wait 1,000 years to see if the ship's adaptations succeed, so we compress centuries of potential crises into days of relentless virtual trial. Computational scientists who build these environments state that the simulation must be a complete universe in miniature, modeling not just the predictable laws of physics, but the chaotic, random nature of the cosmos itself. It has to account for the slow, insidious creep of material fatigue, the complex decision trees of the artificial intelligence, and the sheer statistical weirdness of deep space. The foundation is a hyper-realistic physics engine. This digital realm calculates the subtle effects of microgravity on fluid dynamics in the cooling systems, the way composite materials flex and fatigue under cyclic stress, and the precise impact of a high-energy particle strike on a sensitive circuit. It is a world built from mathematical first principles, where every bolt and wire has a virtual counterpart that behaves exactly as it would in reality. Within this world, the ship's AI undergoes the most grueling training imaginable. Its learning regimens are deliberately cruel, exposing it to a relentless barrage of rare cosmic events. It might face a simulated encounter with an unexpected dust cloud that blinds its sensors, followed immediately by a coronal mass ejection that threatens to fry its electronics. The AI is forced to prioritize, to innovate, and to make life or death decisions with incomplete information, all within the safety of the digital realm. The most profound analysis lies in tracing evolutionary pathways. By running these scenarios in accelerated time, researchers can watch the long-term consequences of the ship's choices unfold over virtual centuries. They might observe a specific self-repair protocol that seems brilliant in the short term, but over hundreds of years leads to a gradual, irreversible depletion of a critical polymer resin. This foresight is priceless, allowing engineers to spot these evolutionary dead ends and program safeguards against them long before the ship is ever built. This virtual proving ground is where we ensure the ship's capacity for change is not a wild, unpredictable force, but a disciplined and reliable tool. It is the final, essential step in building a vessel we can trust not just with a mission, but with the lives of generations to come. These robotic swarms become the ship's tireless hands in the unforgiving vacuum. While the central intelligence calculates and plans, it is this cloud of simple, disposable units that executes the physical work of evolution on the vessel's outer skin. They crawl across the hull like diligent insects, each bot performing a small, specific task that collectively amounts to a major transformation. Their design philosophy is borrowed directly from nature's most successful groups. Robotics engineers do not create one complex, irreplaceable robot for external repairs. Instead, they deploy thousands of simple, identical units, much like a colony of ants or a swarm of bees. Each individual robot is expendable, but the collective is resilient, capable of losing dozens of members without halting its overall mission. They operate on decentralized control, following a set of basic local rules. A bot does not wait for a command from the ship's brain to weld a crack it has found. It simply communicates with its immediate neighbors, and together they coordinate their actions, pooling sensory data to outline the damage, and then swarming over it to begin the repair. This lack of a central controller makes the system incredibly robust. There is no single point of failure for the external modification process. We can break down their capabilities into specialized roles, though many individual robots can switch between these functions. First are the inspection bots. These are the swarm's eyes, equipped with micro cameras and laser scanners. They constantly traverse the hull, creating a living, high-resolution map of the ship's exterior integrity. They identify microfractures, areas of excessive wear, and the subtle pitting caused by cosmic dust long before these issues become critical. Following them are the fabricator drones. These are essentially flying three-dimensional printers. They carry reservoirs of a liquid polymer or a metallic paste. When tasked with repairing a crack or building a new sensor boom, they gather at the site and begin depositing material layer by layer, fusing it in place with tiny lasers or ultraviolet lights. They work in concert, some bots laying down structure while others smooth the surface, collectively printing new parts directly onto the ship's body. Then there are the resource gatherers. these units are designed to venture further out, perhaps to a nearby asteroid or to skim particles from a gas giant's ring system. They collect raw materials which they then process and deliver to the fabricator drones, effectively allowing the ship to grow using resources found along its journey. A powerful analogy for this process is a coral reef. Each individual coral polyp is a simple organism, yet by working together in vast numbers, they construct immense, complex structures that can withstand the ocean's power for millennia. Each polyp secretes its own tiny bit of calcium carbonate, and over time, these small contributions accumulate into a breathtaking underwater landscape. The robotic swarm operates on the same principle. A single welding bot might seal a 1 mm crack, but 10,000 such bots, working in a coordinated ballet, can resurface an entire wing of the spacecraft or assemble a new communications array from a blueprint beamed from the core AI. This collective capability turns the vessel into a continuously sculpted entity. The ship is not a static sculpture frozen at the moment of its launch. It is a dynamic form, its shape and surface properties slowly changing in response to the environment. If navigational data suggests a future course through a region of intense radiation, the swarm might respond by building up additional layers of shielding on that facing hull. If a new scientific instrument is needed to study a passing nebula, the fabricator drones can print and install it on an external hardpoint, all while the voyage continues. This external layer of evolution, made possible by the silent, ceaseless work of the swarm, ensures the ship's physical form never falls behind the wisdom of its mind. The ship's memory is its most sacred trust, a living chronicle etched not in stone but in light and molecules. Every self-repair, every successful adaptation, and every failure analyzed becomes a permanent entry in this vast digital library. This is not a static archive gathering virtual dust. It is the vessel's cumulative intelligence, the hard-won wisdom that allows each generation to stand on the shoulders of those who came before. For a journey spanning centuries, the loss of this knowledge would be a form of collective amnesia, dooming the ship to repeat the same mistakes its ancestors had already solved. The sheer scale of this data demands revolutionary storage. Information scientists working on millennium-long projects point to technologies like synthetic DNA storage, where the entire history of the ship's evolution could be encoded into strands of genetic material, a medium so dense and durable that all of human knowledge could fit in a container the size of a sugar cube. Another approach uses crystalline memory, writing data into the atomic structure of synthetic quartz, a substance that remains stable for millions of years, immune to the radiation and degradation that would destroy conventional hard drives. This ensures the ship's story survives not just for the current crew, but for their descendants who will one day complete the voyage. But storing the data is only the first step. The true genius of the system lies in its active curation. The ship's artificial intelligence does not simply log that a cooling pump failed on a specific date. It logs the environmental conditions that led to the stress, the sequence of attempted repairs, the successful solution, and the long-term performance of the new component. Over time, the AI models distill this raw data into actionable wisdom, identifying deep patterns and causal relationships. It might learn, for instance, that a specific alloy performs poorly in prolonged exposure to a certain type of cosmic radiation, a lesson that will inform material choices for the next 500 years. This living database becomes an interactive tutor for new generations of the crew. A young engineer born on the ship can query the system, asking why a particular corridor has an unusual structural brace. The library does not just provide a schematic, it unfolds the story, showing the simulation of a past gravitational stress event and the iterative design process that led to that specific, elegant solution. It connects the crew to the legacy of their home, fostering a deep, intuitive understanding of the vessel's ever-changing nature. We can see a powerful historical parallel in the great libraries of the ancient world, where scribes meticulously copied scrolls and master craftsmen taught apprentices through hands-on demonstration. This slow, deliberate transfer of engineering knowledge, from building pyramids to forging cathedral arches, allowed cultures to build increasingly complex structures across generations. The starship's memory system automates and perfects this process, creating an unbroken chain of technical and cultural continuity. It ensures that every evolutionary step the ship takes is informed by the entirety of its past, making the vessel not just different as it ages, but genuinely wiser, its intelligence compounding with each light year traveled. The void between stars holds more than just darkness. It is a canvas for phenomena so strange they defy our current understanding of physics. A self-evolving spacecraft must be prepared not just for known dangers, but for the truly alien environments that await. This is the ultimate test of its design, where it must encounter something entirely new and rewrite its own survival manual on the fly. Astrophysicists who study deep space note that regions like dense molecular clouds or the violent neighborhoods around neutron stars present hazards we can only theorize about, from exotic radiation to gravitational distortions. A static ship would be a sitting duck, its pre-programmed defenses suddenly useless. An evolving vessel, however, meets the unknown with a process of active discovery. Its first response is one of intense, focused listening. Advanced sensor suites constantly sample the environment, analyzing the energy signature of a passing nebula or the particle flux from a distant stellar collapse. When these readings fall outside any known classification, the ship's intelligence enters a state of high alert. It begins running comparative analyses, searching its vast memory for even the faintest similarity to past encounters, while simultaneously preparing for the possibility that there is none. This is where its capacity for physical re-engineering becomes critical. The ship might possess reconfigurable magnetic field generators. Faced with a storm of unknown charged particles, the system doesn't just increase power. It experiments, reshaping the magnetic bubble around the hull into a specific, non-standard geometry designed to deflect this new type of threat. A shape born from billions of digital simulations run in the seconds after first contact. The hull itself becomes an active participant. Segments composed of smart materials could alter their opacity, dynamically tuning themselves to block a harmful, specific wavelength of light while remaining transparent to others, protecting internal systems without blinding its own sensors. One of the most elegant adaptations involves using the ship's own mass as a shield. Imagine the sensors detect an incoming wave of high-energy cosmic rays from a previously unobserved source. The artificial intelligence might command a redistribution of the vessel's water stores, pumping thousands of liters from internal tanks to line a specialized compartment in the outer hull. Water rich in hydrogen is an excellent radiation barrier. The ship has just created a temporary, sacrificial buffer, protecting the crew while it analyzes the phenomenon and develops a more permanent solution. This act of improvisation is then logged meticulously. The successful strategy, the radiation's properties, and the effective thickness of the water shield are all encoded into the ship's living memory. The next time it encounters a similar energy signature, even 100 years later, it will recall this hard-won lesson instantly. This capacity transforms the vessel from a mere traveler into a genuine pioneer. It can venture into regions of space that mission planners on Earth would have labeled too risky, because the ship itself possesses the tools to define and manage that risk. It becomes an instrument of discovery, not just a vehicle for it, turning every unforeseen challenge into a new piece of cosmic wisdom that it carries forward into the endless night. The immense orbital shipyard is a cathedral of engineering, a silent hub where modular components are slowly pieced together into a vessel meant to outlive its creators. The economic and logistical hurdles of birthing such a craft are as vast as the space it is destined to cross, while the long-term payoff is a ship that can sustain itself for millennia. The initial investment is a mountain to climb, demanding global cooperation and entirely new ways of thinking about finance. Space industry economists point to models like public-private partnerships, where the resources of governments merge with the agility of corporate innovation. They also discuss intergenerational bonds, financial instruments designed to mature over centuries, allowing the grandchildren of the initial investors to reap the rewards of a successful mission. The ship itself could become a self-sustaining asset, capable of paying back its immense cost by mining rare materials from asteroids or transmitting priceless scientific data back to a waiting Earth. But before that distant return, the upfront costs are staggering. Consider the development of self-healing materials. Qualifying a new metal alloy or polymer for the brutal environment of deep space requires decades of testing in orbital labs and simulated long-duration missions, an endless cycle of failure and refinement that consumes billions. Then there is the monumental expense of artificial intelligence safety validation. Ensuring the ship's mind remains a benevolent guardian requires running millions of complex ethical and operational scenarios in supercomputers for years on end, a digital proving ground that is as costly as it is critical. The logistics of construction are another Herculean challenge. The ship cannot be launched in one piece. It must be built in modular sections, each one launched separately into orbit for final assembly. A delicate orbital ballet requiring a fleet of reusable heavy-lift rockets operating for decades. We have a powerful, if smaller, precedent in the International Space Station. That project required the sustained political will and financial backing of multiple nations working together for over a decade. Our evolving Starship would be that undertaking on a far grander scale, a project not for a single administration or even a single generation, but for all of humanity. This understanding of the immense earthly effort required is a crucial part of the vision. It reminds us that the journey to the stars begins not with a roaring engine, but with quiet determination in laboratories, in boardrooms, and in the collective will of a species looking to its future. The ship's corridors will echo with more than just machinery. They will carry the voices of a new society in the making. This human dimension is the final, and perhaps most complex, system aboard a self-evolving vessel. As generations are born and pass away within its hull, the crew's relationship with their intelligent home will transform. They are not just passengers, they are active participants in a grand, centuries-long experiment in living. The ship's capacity for change will profoundly shape their culture, their laws, and their very identity. Social scientists who model life on these voyages emphasize that governance cannot be a static document drafted on Earth. It must be a living constitution, capable of adapting to the evolving needs and values of the people it serves. The most critical question becomes one of access and control. Who holds the authority to approve or veto the ship's proposed evolutionary steps? A rigid, top-down hierarchy might stifle necessary innovation, while a completely decentralized system could lead to chaos. The solution likely involves a blended model where the ship's AI presents its data-driven proposals to a rotating council of crew members, who then deliberate not just on technical merit, but on social and ethical impact. This creates a continuous dialogue between human intuition and machine logic. Storytelling becomes a vital tool for mission cohesion. The ship's living memory library is not just an engineering log, it is the community's sacred text. The tales of early crews overcoming a critical system failure, or the story of how a particular garden module was redesigned for better community gatherings, become foundational myths. These narratives bind the society together, providing a shared history and a common purpose that transcends individual lifetimes. We can see a powerful parallel in the long sea voyages of the past. Sailors on multi-year journeys developed unique traditions, slang, and social codes entirely distinct from their home ports. They became a culture of their own, shaped by the confines of their ship and the challenges of the ocean. In the same way, the starship's inhabitants will develop their own language, art, and social norms, all influenced by the ever-changing environment of their intelligent home. This cultural evolution will, in turn, guide the ship's physical evolution. If the community begins to highly value communal spaces and artistic expression, they might consistently approve upgrades that expand gardens or create new venues for performance, subtly steering the ship's development away from pure efficiency and toward a greater quality of life. The vessel's transformation becomes a mirror of the people living inside it, a shared journey where every technological leap is weighed against the kind of society they wish to become. A small satellite, no larger than a shoebox, is currently circling our planet with a single, vital mission. It is testing a patch of special polymer that can seal its own punctures, a quiet but profound demonstration of the self-healing principles we have been exploring. This is not a distant vision, it is the tangible beginning. The dream of a self-evolving spacecraft is already unfolding in laboratories and in the vacuum of near-Earth space, with prototypes being tested by both global space agencies and ambitious private companies. Leaders from organizations like DARPA and SpaceX are openly discussing their experiments in autonomous assembly, where small robotic units practice building structures without human guidance. On the International Space Station, astronauts are testing samples of shape memory alloys, metals that can be bent and then returned to their original form with a simple application of heat, a fundamental technology for future ships that can smooth their own dents. One of the most advanced public missions is the Restore-L satellite, designed to demonstrate full in-orbit servicing. This craft is being built to rendezvous with, refuel, and repair other satellites, proving that a spacecraft can act as a mechanic for its peers, a critical skill for a long-duration vessel that must maintain its own health. At the same time, university teams are launching tiny CubeSats that use evolutionary algorithms to manage their orientation. These small brains run thousands of digital simulations to find the most efficient way to control the satellite's position, learning and improving their performance over time. In a recent ground-based test that caught the attention of many engineers, a small, multi-armed robot successfully diagnosed a fault in a simulated solar panel and then performed a complex repair, welding a broken connection with precise, autonomous movements. This achievement, while happening in a warehouse on Earth, is a foundational step. It proves that the physical act of self-repair, guided by an intelligent system, is within our grasp. Each of these projects is a building block: the self-healing polymer, the shape-shifting metal, the learning algorithm. They are all individual pieces of a much larger puzzle. Together, they form a collective proof that the evolutionary spacecraft is not just a theoretical concept, but an engineering goal that is actively being pursued, its first chapters being written in the silent void above us right now. The silence between the stars begins to fill with a quiet conversation, A self-evolving ship, having just learned to harden its hull against a new form of radiation, does not keep this secret to itself. It compresses the entire experience, the sensor data, the failed attempts, the final successful material formula, into a data packet and beams it into the darkness, aimed at the predicted course of another vessel launched decades later. This is the birth of the galactic internet, a network not of websites but of lived experience and hard-won survival wisdom. Each ship becomes a teacher to all the others, ensuring that a solution forged in one corner of the galaxy can benefit every explorer that follows. The evolutionary process, once confined to a single hull, suddenly accelerates across the entire fleet. A ship entering a perilous nebula might receive an update from 3 other vessels that already charted a safe path through it, their collective data painting a real-time map of the hidden dangers. Futurists suggest this could create a kind of distributed consciousness for humanity among the stars, where the intelligence of one becomes the intelligence of all. This requires a universal language for sharing these complex adaptations. Think of it not as a simple radio signal, but as a detailed instruction manual that every ship's artificial intelligence can read and understand. It would describe a new component with standard specifications for its structure, material composition, and the logic behind its design. This shared protocol allows a ship to receive a blueprint for a more efficient water reclamation filter, for instance, and then use its own onboard fabricators to build it, even if the sending ship is a completely different model from a different era. To make this possible across such vast distances, the network would need relay stations. These could be automated outposts placed at strategic gravitational points, like Lagrange points around quiet stars, acting as celestial lighthouses that catch, store, and forward these precious data packets. They would ensure that a message from a ship headed toward the galactic core can eventually reach another journeying toward the rim, preventing the isolation of entire branches of human exploration. This interconnected web also enables a new kind of scouting. A mothership could deploy a swarm of smaller, specialized probes, each one a simplified self-evolving unit. These scouts would fly ahead into an asteroid field or skim the atmosphere of a gas giant, their small swarms allowing them to take risks the main vessel cannot. They would communicate with each other locally, sharing terrain data and identifying safe passages in real time. If one probe is lost to an unexpected plasma jet, the others instantly adjust their formation and continue the survey, sending a continuous stream of refined data back to the mothership. This is the Internet of Things scaled to a cosmic level, where every ship and every probe is a smart device contributing to a single, growing body of knowledge. The ultimate result is a future where humanity's presence in space is no longer dependent on any single, fragile craft. It is maintained by a resilient, adaptive fleet, a learning network that ensures the curiosity and the spirit of those who built the first ships will continue to reach for the stars for millennia to come. So we arrive at a profound realization, one that redefines our relationship with the machines we build. The journey through a self-evolving starship's design reveals a future where resilience is not built in but grown. Adaptation is not programmed but learned. The vessel becomes a seamless blend of biological wisdom and technological prowess, a being whose smart materials form a living skin, whose artificial intelligence acts as a thoughtful mind, and whose ethical safeguards provide a moral compass. This is not merely engineering, it is the birth of a new kind of entity, one that challenges the very boundary we draw between a machine and a living organism. For voyages spanning generations, this capacity for evolution is the only guarantee of survival. It is the difference between a fragile relic and a thriving, intelligent world sailing the void. As we stand at the edge of this new frontier, we must reflect on the legacy we wish to send into the cosmos. We are contemplating the creation of companions for the great dark, vessels that will learn from experiences we cannot imagine and face challenges we will never see. They may one day return to our descendants, not as time capsules from a forgotten past, but as elders bearing wisdom from the depths of space, perhaps even wiser than we who built them. If this vision of a shared future with intelligent, growing starships inspires you, we would love to hear your thoughts. Share your reflections in the comments below and subscribe to join us as we continue to explore the technologies shaping our tomorrow. Together, we can follow these remarkable ships on their journey